Hello, this is Dr. Armand again, bringing you another exciting lecture in chemistry, General Chemistry 1 Laboratories. Today we'll be discussing Lab 8, which is the apparent molecular weight of air. So we'll be looking at the gas laws, in particular the individual gas laws and the ideal gas law. In addition to that, we'll be looking at types of calculations you can do with gas laws, from everything from calculating the pressure, volume, etc. of a gas. In addition, calculating the density and molar mass of a gas. And what we're going to be looking at today are the uh, properties of a gas, namely the pressure, volume, temperature, and amount, and how these gases or how these properties are interdependent with one another and the laws that describe it. So sit back, relax, and enjoy the lecture. So this is lab 8, apparent molecular weight of air. We only have 2 more labs left after this one in our laboratory series, so we're getting near the end. And so we'll be looking at gas laws, and just to kind of summarize the different properties of gases, there are 4 ways you can describe a gas. You can describe a gas from its pressure, temperature, volume, and amount. Now, for some of these quantities, when we're dealing with measurements, we have common measurements that we use. However, when we're dealing with calculations, there are certain units that we need. So for measuring, there are some common units that we use. For calculations, in some examples, I'm going to tell you that it has to be in these particular units. So make sure they're in those units. So first off, we have pressure, and we'll talk more about what pressure is in just a moment, but pressure is generally measured in millimeters of mercury or torr. Now, if you ever watch the weather on the local news, sometimes they talk about the atmospheric pressure in inches of mercury. Here we have millimeters of mercury, so you're right to go from millimeters of mercury to inches of mercury. You can just use a conversion factor like you do going from millimeters to inches. Now, generally, pressure is measured in these units. However, in some equations that involve calculating different properties, pressure has to be in atmospheres. And that equation that uses atmospheres for pressure is the ideal gas equation. So anytime you use the ideal gas equation, pressure has to be in ATM. And this is because, as we'll see in a little bit, the ideal gas constant is in ATM, so therefore our pressure has to be in ATM. Next, we look at the property temperature. Temperature in the laboratory is measured in degrees Celsius. However, for all calculations involving calculating the temperature of a gas, temperature needs to be in Kelvin. And so this is for all equations. Anytime you see temperature involving a gas and you have to put it in an equation, you need to convert it to Kelvin. And the reason is Kelvin is an absolute temperature. There's no negative Kelvin. 0 Kelvin is as low as you can go. And so here, if we look at a temperature unit needs to be Kelvin. For all gas equation. Now, maybe you don't remember this from if you're taking the Jenkin 1 Jenkin 1 lecture, the way you convert to Kelvin is equal to 273.15 plus the degrees Celsius. So if you know your degrees Celsius, you add 273.15, you get the Kelvin. Now for volume, common units that we use in the laboratory are milliliters, depending on the quantity of the gas you're going to measure, but generally for chemistry laboratories, gases are usually measured in milliliters. However, there are some calculations where the unit of volume needs to be in liters. and that's for the ideal gas equation. For the ideal gas equation, volume needs to be in liters. Now, for other gas equations, it doesn't matter for the individual gas laws. But for the ideal gas equation, volume needs to be in liters because the ideal gas constant units have liters in it. For amount, as you should be, obviously you should know, is that when we measure in the lab, we're measured in grams. However, for most calculations, we're dealing with moles, unless you're trying to calculate the mass of a gas or the molar mass of a gas. But for most calculations, we're using moles. So you always need to convert mass to moles in that case. Now, these are all interdependent on one another, and we're going to talk about that, what that means in just a second. So, for example, how does pressure behave with changing temperature at constant volume in moles? So we're going to look at the interdependency of all these different properties or variables of gases. And that's where the individual gas laws come into play. Now, when we're talking about gases, generally we describe them as ideal gases. And this means that these gases have a linear relationship among the different quantities or properties of a gas. Now, while no ideal gas exists, there are some gases that can behave very close to ideal gas behavior at very common temperature and pressure. Now, when we say the gases have a linear relationship among the different properties, is if we have a graph, and let's say we're plotting pressure versus temperature, what we're going to see is we're going to see a straight line. As we increase pressure, we're going to increase the temperature of the gas, and this is at constant volume in moles. So if you hold the volume constant and you hold the amount of gas constant, as you increase the temperature, you're going to see an increase in pressure, and you get this linear curve. And that's what we mean when we say has a linear relationship among them. One other thing to remember in dealing with gases is that some gases are diatomic molecules. So when you're reading a problem and it says we use, for example, hydrogen gas, hydrogen is a diatomic molecule, so it would be H2. So what does it mean, diatomic molecules? It means it's made up of two atoms. And so these are things like, these are gases like hydrogen gas, or elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These exist as diatomic molecules. That means when you write the formula of, say, oxygen gas, it would be O2. You write the formula of fluorine gas, it would be F2. And this is a common mistake that students make, is when they're talking about a particular gas that involves diatomic molecules, they'll just put O instead of O2. You got to remember that these elements exist as diatomic molecules, and you need to write the correct formula for it. So what is gas pressure? So the gas pressure results as the molecules collide with the walls of the container that the gas is in. So these molecules are flying around in a container. When they hit the walls of the container, that's where you get gas pressure. And so pressure mathematically is the force over a particular area. So if you know the force, so the molecule is coming with some force, it hits a particular area in the container, that's where we get the pressure from. Now, there are two types of apparatuses to measure pressure. If we're measuring atmospheric pressure, it's a barometer. So what we have here in the lower right-hand corner is a barometer. So the atmospheric pressure pushes down on the pool of mercury, which causes the mercury to go up the tube. And this tube is graduated in millimeters. So each one of these dashes represents a millimeter. So if you can, or represents millimeters. So if you measure the distance the mercury traveled, that's where we get the pressure of the atmosphere. And that's where it comes from, millimeters of mercury, because each one of these dashes is millimeters. And as we'll talk about later, millimeters of mercury is a common unit for pressure. Now, for experiments involving gases, typically we use a manometer, which measures the gas pressure in experiments. And so you can have different types. You can have a closed-in manometer, means it's sealed off. You have your initial height of the liquid. As you do your reaction, the gas pressure builds up in the tube, pushes the liquid higher. So the difference between the before and after gives you the pressure of the gas. Now with open-ended manometers, we have the height of the pressure of the gas and the height of the pH2. So the two of these add together to determine the pressure, the atmospheric pressure. So the atmospheric pressure is pushing down, and we know the change in height. We can calculate the pressure of a gas. Now there are many different units of pressure, and I'm just going to give you a few of them, some of the more common ones. So the SI unit for pressure is what's called a Pascal, PA. And if you remember, pressure is the force per area. So a Pascal is a Newton per meter squared. Newton is a unit of force. And meters squared is a unit of area. And that's where you get force over area gives you pressure. And we generally don't use pascals that much, but it is the SI unit. It's a derived unit, a derived SI unit. One of the more common units of pressure we use is atmospheres, which is the atmospheric pressure measured at sea level, and it's at 0 degrees Celsius. Now, 1 atmosphere equals 101.325 kilopascals, and that's how you convert atmospheres back to pascals. Now, this is not an exact number, it's a measured number, so you have to include that in we're looking at significant figures. Now, millimeters of mercury were sometimes referred to as torr if the temperature is not at 0 degrees Celsius. So this is a technicality. So if you're at 0 degrees Celsius, it's referred to as millimeters of mercury. Generally, if you're at other temperatures other than 0 degrees Celsius, it's referred to as torr. Now, as we were explaining earlier how the barometer works, the atmospheric pressure pushes down on this pool of mercury. The mercury goes up the tube, and you're measuring the height of the mercury in using a graduation, which is in millimeters, and that's where millimeters of mercury come from. This is probably one of the most common units of pressure used in chemistry, and so it's very important that you know atmospheres and millimeters of mercury. Now, 1 atmosphere is 760 millimeters of mercury, or 760 torr. These are exact conversions. So you need to know these conversions for converting from millimeters of mercury torr to atmospheres. Some other less common pressure units is the bar. So 1 bar is 100 kilopascals. And then one that you might be familiar with is PSI, which is pounds per square inch. This is if you ever added air to your tires. Generally, tire pressure in a normal regular tire is 34 or 32 to 36 psi. And so to convert from atmospheres to psi, we use this conversion here, 14.7 psi 1 atmosphere. So this is the different units of gas pressure. Now we're going to be talking about the interdependency of the different units of or different quantities of a gas. The first one we're going to talk about is Boyles Law, and this is a picture of Mr. Boyle here. And most of these individual gas laws were developed by scientists, I would say anywhere between the 17th and 18th centuries. And so Boyles Law relates pressure and volume at constant, and it has to be constant, temperature and moles. So if you're at constant temperature and moles, and you want to know how the volume relates to the pressure of a gas, we use this equation here, which tells us that the volume is inversely related to pressure. So Boyles Law relates pressure and volume, and it states that they're inversely related. So that means as volume increases, pressure is going to decrease because they're inversely related. So now if we took this, you can also rewrite it as P equals K divided by V. You may see it written either way, it's still the same. So now if we plot the pressure versus 1 over V, we would get a straight line, and the slope of this line would equal K. Now, if you know the pressure and volume of a gas, and you want to change the pressure, let's say we change the pressure, we want to calculate the new volume, we would use this equation here. Again, this equation is used when you have a pressure and volume of a gas. You change one of those two properties at constant temperature in moles, you would use this equation. And at the end of this, we'll do some examples involving individual gas laws. Now, this picture down here is illustrating Boyles Law. The weights signify pressure. The cylinder signifies volume. The dots or the spheres represent the amounts. There's the same number of spheres in each one of these diagrams. The blue color signifies temperature, so it's the same temperature. As we increase the pressure by adding more weights, you see that the volume decreases respectively. Real life example of this, if you go scuba diving, you close it before you jump into the ocean. You close a bottle, you seal it. Now as you go down the depths of the ocean, as you go deeper into the ocean, the pressure increases. So as pressure increases, volume would decrease. And this would cause the bottle to crush. Next law is the Charles's law, which relates, in this case, volume and temperature. So it states that if you have a change in volume at constant pressure and moles, temperature will react this way. So again, this is at constant. Let me erase that. This is at constant pressure and moles. And you may ask, well, how do I know in a problem if it's at constant pressure and moles? The way you would know this is either A, it doesn't mention anything about the pressure or moles. B, it could be that it says it's, for example, in a sealed container. So if it's in a sealed container, the moles is constant. Or C, you could just say at the end of the problem, it's at constant pressure. And so this is the equation that we use to show the relationship between volume and temperature at constant pressure in moles. This is saying that they're directly related. So if you increase the volume of a gas at constant pressure in moles, you're going to increase the temperature of a gas. So they're directly related. As you increase one, the other increases as well. So we look at a graph of this and we plot volume versus temperature. Remember, temperature has to be in what unit? That's right, it has to be in Kelvin. As we plot this, as we increase temperature, volume will increase as well. Now remember, the slope here will equal K. Now if you know the volume and the temperature of a gas, and you want to say change the temperature, Then you can calculate what the new volume would be. Now in this equation, temperature has to be in Kelvin. So make sure anytime you use this equation, temperature is in Kelvin before you do it, or else you'll get the incorrect answer. You may even get a negative volume, which, what is negative volume? I don't know. It's like a volume within itself, kind of like maybe a black hole. I don't know. That's interesting. So make sure you convert it to Kelvin. Now down here in these diagrams, what we're seeing here is the cylinder again represents volume. Notice here there's no weights, so there's no change in pressure. We have the same number of spheres, so it's constant amount. And you see that the color is different. So this is blue and this is yellow. So that means we've changed the temperature. We went from negative 65 degrees Celsius to 250 degrees Celsius. So since we increase the temperature, the volume increases. And so Charles's law relates temperature and volume at constant pressure in moles. An example, a real life example of this, I don't know how real life it is unless you have liquid nitrogen lying around, but this is liquid nitrogen, liquid N2. You have a balloon, you put the balloon in the liquid nitrogen, it's very cold, so what you're doing is you're rapidly decreasing the temperature at constant pressure in moles. So what happens? If you decrease the temperature, you're going to decrease the volume. And so over time, the balloon shrinks, and when you take it out of the liquid nitrogen, and as it heats up, it actually expands again. Now, if you don't have liquid nitrogen, you can always take a balloon, blow it up, stick it in the back of your freezer, leave it for a few weeks or a month, and you'll see over time that the balloon will shrink. Now, Gaylus Law is kind of like combining, or is based off, I shouldn't say, based off Boyles and Charles' law. So Boyles' law relates pressure and volume, says they're inversely related. Charles' law relates volume and temperature, says they're directly related. So Gaylus law relates absolute temperature, which means it's Kelvin, and pressure. And this is at constant volume and moles. So at constant volumes and moles, we see that pressure is directly related to temperature. So if we were to increase pressure at constant volume and moles, we would increase the temperature of a gas. Now, a kind of a close example of this would be if you took, those cans of compressed air that you use to clean your what's it called? The computer screen. So as you spray it over time, the can gets cold and it stops working, because what's happening is as you're spraying the compressed air, the pressure inside the container decreases. So as it decreases, the temperature decreases as well. Likewise, some of you may have encountered this, but on a very cold morning, you may go to your car and the tire light comes on. So what's happened is that it's so cold outside, the gas or the air in your tire, since it's at constant volume and amount, since the temperature decreases, it causes the pressure to decrease, which then causes the sensor in your tire to determine that, hey, this tire is low. So if that happens, just go put some air in your tire, the light will go off. Now, if we plot pressure versus temperature, and again, temperature needs to be in what unit? Kelvin, that's correct. We get a linear relationship. And again, the slope equals K. Now, if we know the pressure and temperature of the gas, and we change the temperature of the gas, let me undo that. And we change the temperature of the gas, we can calculate the new pressure using this equation here. Now, one thing you need to remember is that temperature needs to be in Kelvin. So make sure you convert to Kelvin first before you put it into this equation as well. So the diagram here, what we're seeing is the half human and whole human and two humans. This is increasing pressure. Now the box symbolizes constant volume. The number of spheres in the boxes symbolizes constant amount, and the candles symbolize increase in temperature. So as you increase the temperature, you increase the pressure at constant volume and amount. Now, if we take Boyles Law and we take Charles's Law and combine them, we get something called the Combined Gas Law. And so the Combined Gas Law is V equals, we use the relationship, the volume is directly related to the temperature, but inversely related to the pressure at constant moles. The only thing constant here is the moles. Everything else changes. And so if we know the pressure, the volume, and the temperature of the gas, and then we come and we change the pressure and the volume, we can calculate the new temperature of the gas. Excuse me. And what you need to remember is that temperature needs to be in Kelvin. So make sure you convert T to Kelvin. Now the last individual gas law we're going to talk about excuse me, is Avogadros gas law. And this is the same Avogadro that determined Avogadro's constant, or that's what same Avogadro that Avogadro's constant is named after. And Avogadro's law relates the volume to the amount at constant pressure and T. And so if we know the volume and we're at constant pressure and T, we can look at the relationship between the volume and the amounts. And so as we increase volume, we're going to increase the amount and vice versa at constant pressure and temperature. So now if we plot volume versus moles, we're going to get a linear relationship, and the slope equals K. Now if you know the volume and the amount of the gas, and let's say we change the amount of gas, we can calculate the new volume. Now this little cartoon over here is about Avogadro, because remember I told you Avogadro, same Avogadro that Avogadro's number is named after. And so this little meme says, I just met you and this is crazy, but here's my number, 6.022 times 10 to the 23rd, so mow me maybe. And that's a take on an old song that maybe you've heard before, but I kind of like it, that's why I put it in. So one of the things we got to remember about gases is that gases, sometimes we experiment with them at what we call standard conditions, or we do calculations at standard conditions. And so what is a standard condition for a gas? So there's standard temperature, pressure, even moles and molar volume of a gas. Now standard temperature and pressure is commonly referred to as STP. So STP doesn't stand for, in this case, scientifically treated petroleum. It stands for standard temperature and pressure of a gas. So the standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atm, or you could say 760 millimeters of mercury. The molar volume is based on the standard amount, which is 1 mole of gas at STP, and the molar volume is 22.4 liters. So if you had 2 moles of gas, And this can be 2 moles of any gas. 2 moles of gas at STP would occupy, what was that? 44.8 liters. It would just be double the molar volume of 1 mole of gas. And so whenever we talk about standard conditions of a gas, these are the conditions we're referring to. So now if we take Boyles Law, Charles's Law, and Avogadros Law, we have all these individual gas laws. If we combine them, we get one law to rule them all. I don't know if you know my play on that words right there, but that comes from Lord of the Rings. One ring, isn't it? One ring to rule them all? I'm not sure. Anyways, if you take all 3 of these laws and you combine them, you get what's called the ideal gas law, which is one law to rule them all. So you can derive all the individual gas laws from the ideal gas law. And so P, of course, stands for pressure. V is for volume, and pressure here needs to be in ATM. Always ATM, and we'll explain why in a second. Volume needs to always be in liters. Of course, N is the number of moles. R is the gas constant. We'll talk about that in just a second. And temperature needs to be in what unit? That's right, it needs to be in Kelvin. And so R is the gas constant, and it's determined by taking the standard conditions that we talked about on the other slide and plugging them into the ideal gas equation to solve for R. So since our pressure is 1 atmosphere, our volume is 22.4 liters, N is 1 mole, T is 273 Kelvin. When you plug all that in, you get the ideal gas constant that is in atmospheres, liters per mole Kelvin. And this gas constant never changes when using the ideal gas equation. It's always going to be 0.0821 atmospheres liters per mole Kelvin. Now, you use the ideal gas law when you're given, say, 3 of the properties of a gas and you're asked to convert the 4th. The individual gas laws are when you're given 2 or 3 properties of the gas, you change 2 of them or 1 of them, and you're asked to calculate what's the new quantity. So here we have a gas at negative 25 degrees Celsius, 5.5 liters. It expands to a volume of 12.5 liters. What's the temperature of the gas? And we want to know in degrees Celsius. Assume the pressure and amount of the gas remains constant. So since temperature and volume are changing, we're going to be using V1 over T1 equals V2 over T2. Remember that temperature needs to be in Kelvin. So the first thing we're going to do is we're going to convert each temperature to Kelvin. So T1 is 273.15 minus 25. So 248.15 Kelvin. T2 is what we're looking for. And V1 is the volume at negative 25 degrees Celsius. And V2 is 12.5. Now what we see here is what are we doing to the volume? So in this case, the volume is increasing. So our final temperature should also increase. So our temperature should be greater than negative 25 degrees Celsius. So now we plug this in. We get 5.50 divided by 248.15 equals 12.5 divided by T2. So we get T2 equals 5.5 times 12.5 divided by 248.15. T2 equals Oops, I made a boo-boo. Did my algebra wrong. So T2 equals, I got this backwards, it should be 248.15 times 12.5 divided by 5.5. And so we get about 564 Kelvin. And then we got to convert this to degrees Celsius by subtracting 273 from it, for 564 minus 273.5. So we get about 291 degrees C. And so that would be the new temperature of the gas. All right. Next we have another, and again, you know these are individual gas law problems because properties are changing, other properties are held constant. So in this example, we have a gas at 350 millimeters of mercury, 7.35 liters. We contracts, and it contracts to a volume of 2.55 liters. What is the pressure of the gas? And it assumes temperature and amount remains constant. So here, since pressure and volume are changing, we're going to be using Boyles Law. So P1 V1 equals P2 V2. Now, all we have to do here is make sure that pressure and volume for both sides is the same. So we want P1 and P2 to be the same unit, and we want V1 and V2 to be the same unit. Doesn't matter what unit they are, but the same. And so what we're seeing here in this equation, we know that P1 is 350 millimeters of mercury. V1 is 3.75 liters. P2 is what we're looking for. V2 is 2.55 liters. So what's happening is volume is decreasing, and Boyles Law states that pressure and volume are inversely related. So if volume decreases, pressure has to increase. So now if we set this up, we get 350 times 3.75 equals P2 times 2.55. So we get that P2 equals 350 times 3.75. And so we get that the pressure is 515 millimeters of mercury. So that makes sense. As we decrease the volume, the pressure increased. So those were individual gas laws. Here we were looking at an example where we have a balloon filled with 2.5 kilograms of hydrogen gas. And note here it says hydrogen gas. If you remember from the first slide, hydrogen gas is diatomic, so the formula of this is H2. at a pressure of 835 millimeters of mercury and negative 15 degrees Celsius. What is the volume of the balloon under these conditions? So in this example, we're not changing anything. We're just saying, based on these conditions, calculate this quantity of the gas. So we're going to be using PV equals nRT, and we're going to be solving for V. V equals nRT divided by P. Again, R is the gas constant. R equals 0.0821. Now, N is the moles. We don't know yet. P is the pressure, 835 millimeters of mercury. We're going to convert this to atmospheres by dividing by 760. And by the way, when you do this conversion, please don't round too much. Take quite a few significant figures, because if you round too much, it could cause significant error in your answer. Temperature is negative 15 degrees C. We got to convert this to Kelvin. We get 258.15 Kelvin. So the only thing we're missing is the amount. Now we know the mass is 2.5 kilograms, which is 2,500 grams. So from that we can calculate the moles, which is 2,500 divided by 2. 1,250 moles. Now that we have all the correct units, we can plug it in. So we get V equals so volume equals about 24,110. That'll be somewhere around there. I mean, if you're like 114, 109, that's fine too. And so that's the volume of the gas. So there are some other properties that we can calculate for a gas by rearranging the ideal gas law. And one of these properties is the density of a gas. So what I have here is, I have the ideal gas law, I have the density equation, and I have the equation for the calculate moles from mass and molar mass. So if we start out with the ideal gas equation, PV equals nRT, and we replace N with mass over molar mass, we get PV equals mRT divided by molar mass. If we rearrange this, we get M over V equals P times the molar mass divided by RT. So if you know the pressure of a gas, you know its molar mass, and temperature, you can calculate the density of a gas. And so again, this would be density. And density of a gas is in the units grams per liter. Now what this states is that as the pressure of a gas increases, you're going to increase its density. As the temperature of a gas increases, you're actually going to decrease density. So as pressure increases, density would increase for the gas. Now, as temperature increases, which is based on the equation here, the density would decrease for a gas. Likewise, the heavier the gas is, the greater the density would be. Now, another property you can calculate is the molar mass of a gas. So if we take PV equals MRT divided by molar mass, we get that the molar mass equals MRT divided by PV. And again, the molar mass is in units of grams per mole. So these are the two additional calculations we can do that involve the ideal gas equation. So here we want to calculate the density of nitrogen gas at 0.75 atmospheres and negative 35 degrees Celsius. So here we're dealing with nitrogen gas. Remember nitrogen gas, what's special about it? That's correct, it's diatomic. N2. We want to calculate the density of a gas. So density is the pressure times the molar mass divided by RT. The pressure's in atmospheres, that's good. Temperature, we got to convert to Kelvin. We get 238.15. The molar mass is 28 grams per mole because it's diatomic, and R is 0.0821. Too many zeros there. 0.821 liter atmosphere per mole Kelvin. Now we can plug it in. So we got the density equals and we get 1.07 grams per liter. And somewhere around in there, it's going to be maybe 1.08 is fine, 1.06 is fine, just in that ballpark. And that's how you calculate the density of a gas. So here we have a sample of sulfur vapor, has a mass of 0.385 grams at a pressure of 294 torr. 405 milliliters of the gas is the volume and 45 degrees Celsius. What is the molecular formula of sulfur vapor? So since we're looking for the molecular formula, that's what we're looking for. Now, if we reflect back to early on when we talked about empirical formulas, molecular formula is equal to N times the empirical formula. So what is the empirical formula of sulfur vapor? It's just S. And so we know the molar mass of empirical formula equals 32 grams per mole. Now to find the molecular formula, we got to know what N is, and N is the molar mass of molecular formula divided by molar mass of empirical formula. So what we need to know is the molar mass of the molecular formula. We're going to use the ideal gas equation to determine that. So we know that molar mass equals MRT divided by PV. So if we know the mass, the temperature, the pressure, and volume of a gas, we can calculate its molar mass. So the mass is 0.385 grams. R, of course, is the ideal gas constant. Temperature is 45 degrees C. We got to convert to Kelvin. Pressure is 294.1 torr. We got to convert to atmospheres by dividing by 760. Make sure you put quite a few significant figures in this one because you don't want an error associated with the rounding. And then volume needs to be in liters. Now that we have all this, we can plug it in. So molar mass get the molar mass to be about 64.17. Now we can find N. And this is approximately, let me just do it. Get 2.00, approximately 2. So this says the molecular formula is S2. And so here we're using the ideal gas equation to help us determine the molecular formula of a gas. So what's the to-do list for this lab? Well, make sure you read over the lab lecture notes and watch the lab lecture video, very important. Read over the background information of this lab on the Hayden McNeil virtual lab site. Then I would recommend completing the lab lecture quiz for this lab. Make sure you remember the diatomic molecules. They exist as pairs of 2. Then complete the virtual lab, and then finally complete the post lab for this experiment on Blackboard. So on that note, I hope you enjoyed today's lecture. If you did enjoy it or you learned something new, it's always nice if you hit the like button at the bottom. But on that note, until next time, Dr. Armand is signing off.